So how is the curl of the gradient of voltage not equal to 0? This is a predicament that comes up from the Maxwell equations that we can show minus gradient of voltage equals the electric field. And you can check the units for this if you want. Spatial derivative operator will just divide it by length. So now we can look at the curl of E, which Maxwell equations give us, and I guess this would be Faraday's law, minus partial B partial T. And B is the magnetic field, also a vector quantity. So we can tell, and I'll plug it in just to be sure, but we can tell that if we take the curl of the gradient of voltage, so first that equals the curl of the minus electric field, and then again you can just keep the negative out. This will give us partial B, partial T. No negative this time because they cancel. So we can tell very quickly this is not equal to 0. So what gives? So we start by saying that partial B, partial T is something that has the partial derivative with respect to time has nothing to do with the partial derivative with respect to space. So these are already fundamentally different units, and we can keep going. But let's just start by talking more about the identity that the curl of a gradient of a scalar field should equal 0. So another vector identity is that the divergence of the curl of some vector field, let's call it A, must equal 0. And we know from the Maxwell equations that the divergence of the magnetic field is equal to 0. This just means that there's complete loops in the vector field and there's no sinks or sources. So, now, what if we represented B, the B field, because we know that its divergence is 0, just like a curl field? Let's say that B is now equal to gradient cross A, which is a vector quantity, vector field. So this is what we define as the magnetic potential, but don't worry about the language about it. Let's just see what we can do if we define B as gradient cross A. So let's plug this in to partial B, partial T. So now we'll get, I'll move back over here. Gradient cross E equals minus partial T of gradient cross A. And derivatives like this can be in any order. They don't care which partial derivative is taken first. So now that we can see this, let's go back up. Let's start working our way up to why the curl of the gradient of voltage wouldn't be equal to 0. So let's take gradient cross gradient B equals minus partial T. I'm going to erase this. Of gradient cross A. Well, the interesting thing about this is the spatial derivatives do not matter the order. Neither does the time derivative here, as long as the scalar field in question is continuous everywhere. So now let's start by moving these derivatives. So we have partial A, partial T, and then minus, doesn't matter though, equals, and forgot to bring that out, curl of the minus partial A, partial T equals the curl of the gradient of voltage. And now we can see very easily that the curl and the curl on both sides, so we can just erase. So now we have, and I'll write it bigger. We have that gradient V equals minus partial A partial t. And this right here, this is relating a spatial derivative to a time derivative. So these are actually not of the same language that would happen if you kept taking spatial derivatives. So even though it should be equal to 0 at this scale, that's only if time is not a function. It's only changing through space. But it is changing through time if we're changing the magnetic field, which would in turn change A, because A is defined as the gradient cross A. So this would give us that we add this to our original equation, minus gradient V equals E. Well, we have that gradient of V also equals minus partial A partial t via this definition. So we would know that E, and we'll change the sign on this, minus the gradient of voltage equals E plus partial A partial t. And this is the term that can survive all of the spatial derivatives. Thank you.